Welcome to day 14. You've got your first two homework answers there for 1A and 1B. We'll scroll down in a second. For the review sheet, worked out answers are posted on Schoology. So as you are working and reviewing through those, you can be checking them there. First two homework ones, we just wanted the horizontal component and vertical component. We had initial velocity at 80, we had angle of 30. So you see those filled in the first line, and then just the trig functions evaluated. The cos 30 and sine 30 gives us our neatened up versions on those last lines for A and B. In C, we wanted to know when the maximum height occurred. Well, when that maximum height is occurring, there should be a tangent line slope of 0. So take the derivative of your y component. That would lead to a horizontal tangent line when we set it equal to 0, and we get 5/4 seconds or 1.25 seconds. In D, we want to know what is that maximum height. So plug our answer from C into your y component, your vertical component, to get our maximum height of 29 feet. In E, we know that it's a horizontal distance of 46 when it will be over the pitcher's head. So set your horizontal component equal to 46 and solve for t. Now we know the time that the ball will reach that horizontal distance. Put that time into the vertical part, and that will give you the actual height the ball is at that time. So it looks like it'll safely be over the pitcher's head. Go to the next one. We want to know what is the maximum height. So again, take the derivative of your y component, set it equal to 0, solve for t. We get that 5/4 sine of 40. That's the time when the maximum height occurs. Sub that into your y equation, and that tells you what the actual maximum height is. In B, we want to know how far away it is when it hits the ground. Well, we know that when it hits the ground, the height is 0. So first take your y equation, set it equal to 0. Now, we're assuming, because they didn't give us an initial height, that it started from 0 for our initial height at the end of that equation. You can pull out a negative 8t, set them each equal to 0. The t equals 0 is when it started, when it first left the ground. So we're interested in that 5/2 sine 40. So that's the time when it's going to hit the ground. Fill that value of t into the x equation, and that'll give you the horizontal distance that it travels. Three is a tricky one. So we only know our angle, and we've got an initial height at ground level, so the initial height is 0. Then we want to know what initial velocity will make it travel a horizontal distance of 100. So put 100 in for your x in your x equation. We're going to work to get t by itself. And notice you're just carrying your initial velocity v0 through. Take that time, sub it in over here. These v0s wipe out. So now v0 is just in one location. So you basically had to work through, get the v0 by itself eventually, and then round it to our nearest hundredth they asked for in the question. So that was 96.73 feet per second. Well, then they wanted to know in part B, the distance traveled by our projectile. Well, our 96.73 was a feet per second. This 100 was a feet. So we can divide them to get the number of seconds that the projectile travels. Then we can do our arc length formula from 0 to that 1.050. Where under our radical, we have our x derivative squared plus our y derivative squared. Put that in the calculator, and we get 100.540 feet. Now we've got vector valued functions. So plug in 0, 1, 2, 3, 4 for t. Put your arrows on to show the direction it's going. Then the length, we're just doing from 0 to 4 the square root of our x derivative, or sorry, square root of our x derivative squared plus our y derivative squared. Do your integral, you should eventually get 4 radical 10. Stub in your values of theta from 0 to 2 pi. We should get a circle there. So then our length, do your x derivative squared plus the y derivative squared all under a square root. We're going 0 to 2 pi. Now this one neatened up pretty nicely. They would each have an a squared. You could pull that out. Square root of a squared is absolute value of a, but because we're 0 to 2 pi, it would be a positive a. And then the sine squared plus cos squared under the square root would give you 1. That's why we only have a left there. Then do your antiderivative, you get at. Fill in, you eventually get 2a pi. Plot your values for 0 to pi over 2. It should look something like that. Put your arrows on for the direction you're going. You've got your x derivative squared plus your y derivative squared all under the square root. That's not something we can do nicely, so we just put it in the calculator. We get 7.090. And the textbook one, that's a picture of what our graph looks like. So this is our first one. That's our second one. And we wanted to find this space here. Well, notice we've essentially got 4 sections that are that size. So we can find the area of just one of those and multiply it by 4. So you really have the option of doing any of those 4 sections. I did that yellow one that I traced in the green. So in our green, which is the one with the 1 minus sine theta, when you put in 0, you get back 3. So it's starting here. Then when you put in pi over 2, you get back 0. So we're going 0 to pi over 2 for that. That's where I get my bounds. We have 1/2 our radius squared d theta. And it's up to you. You can either put the 4 times here, because we know we want 4 of them, or I just noted that we have to multiply by 4, and I just remembered, okay, we got to do 4 times that at the end. It's your choice, but just don't forget to put the 4 times that in somewhere. You had a power reduction you had to do, obviously, with these, and then we'll leave that up for a second to check your steps in case you need to fix anything. All right, so let's go in our notes packet. This unit was very formula based, so we're going to run through all of the formulas so that you have them on 2 consecutive pages in the notes packet. So slope of a parametric, keep in mind, we need it to be a smooth curve. And dy dx is just equal to dy dt over dx dt. If you ever wanted to know where it had a horizontal tangent, we wanted the numerator to be 0, vertical tangent denominator to be 0. Second derivative to determine concavity. We do our derivative with respect to t of our first derivative, dy dx, and then over dx dt. Arc length, just a reminder, smooth. So sometimes with arc length, you might just have to do one section and multiply it by how many of the sections are alike. Okay, it can't intersect itself other than at the endpoints. So just keep that in mind for arc length. So for that, we just had our integral from a to b. We had our square root of dx dt squared plus dy dt squared with a dt at the end. And our surface area, we had two scenarios if we were spinning it over the x-axis or the y-axis. Both were 2 pi radius times arc length. So the x-axis one was 2 pi. If we're going over the x-axis, our radius was our y of t. Keep in mind that's not the derivative, that's actually y itself. And then we just have our arc length, the same thing we wrote above. And then the only thing that changes for the y-axis one is our radius would now be going right to left, so it is your x part of the parametric. So that was the first topic, looking at parametrics. Next we did polar. So a reminder with polar, when doing the slope, first think of it as x equals r cos theta and y equals r sine theta, where r was really some function of theta. So it's some function of theta times cos theta, and y is some function of theta times sine theta. And the question will tell you what r equals. So if we want to have dy dx, we have to do a product rule. So for the y's, we'll maybe do derivative times regular plus regular times derivative. Oops. And then for the x's, we'll do the same thing. So we'll do derivative times regular plus regular times, our derivative would be negative sine theta. Our area from A to B, usually we put the 1/2 out front. And then you have whatever your radius function is in terms of theta squared with a d theta on the end. Your length of a polar curve, we had square root like we have in all of our links, but we had our original radius function squared plus the derivative squared with a d theta on the end. And in addition to the x equals r cos theta, y equals r sine theta, if you wanted to write it as a reminder that we have r squared equals x squared plus y squared, we also have tan theta equals y over x, or you could think of it as theta equals tan inverse of y over x as well. All right, going over to the next page, we'll look at our vector valued functions. So if you're doing your derivative, you just take the derivative of each part. If you're doing the integral, you just do your integral of each part. Now just keep in mind when doing those integrals, a lot of times you have to resolve your plus c. Length of a vector valued function, pretty much the same as our parametric one. We've got from A to B. Square root, you've got your dx dt all squared. dy dt all squared. With a dt at the end. Projectile motion for your x and y components. The x component was really v0 cos of t. So that's what we saw on last night's homework. And then the y component is really negative 1/2 gravity constant t squared plus v0 sine of t, sorry, sine of theta times t, and then plus your initial height. And you could have it written as a vector valued function. We saw some on the homework where we just wrote the x and the y separately. You could do that as well. I need to fix something. Sorry. This is cos theta and then times t. So your speed, you've got your magnitude of either r prime of t, or that's the same as saying the magnitude of v of t, if we're calling it a velocity. And that would equal the square root of x prime of t squared plus y prime of t squared. So notice it's essentially the same as the arc length formula, but there's no integral because we'd be doing it at one specific time. And let's add one last thing on here. If you did your limit as t approaches a of some vector valued function r of t, that's just equal to the limit as t approaches a of your x component, comma, your limit as t approaches a of your y component. So we're going to look at some select ones from the review sheet. In most cases, you'll probably need to do it on a separate sheet of paper, so you might want to just have some separate paper out to work through it. We're going to start with number 1. So we want to eliminate the parameter. Now, it's a little annoying, but there's a couple questions where the equations wrap around on the line. So notice it says plus, and then the 1 goes to the bottom. So this is really y equals 2t plus 1. So I apologize for that with the formatting. So of these two, it's probably going to be easier to get t by itself in the y1. So we can subtract the 1 over, divide by 2. We got y minus 1 over 2 equals t. So let's fill that in our x component. So this is really x equals 3 times, we're going to have y squared minus 2y plus 1 all over 4. So let's do two things. Let's multiply the 4 over and distribute the 3 through. So we'll get 4x is equal to 3y squared minus 6y plus 3. And to get it to match with one of our choices, let's subtract the 4x over. So we have 3y squared minus 4x minus 6y plus 3. And that looks like it matches with choice B. Let's go over to number 2, another eliminate the parameter one, but we've got trig. We want to get the sine and cosine by itself, so we have x minus 1 equals cos theta. y minus 2 equals negative sine theta. So then divide by negative, and you get negative y plus 2 equals sine theta. So we're doing our Pythagorean property that sine squared theta plus cos squared theta equals 1. I'm just going to do the cos squared stuff first. We'll have x minus 1 squared plus negative y plus 2 all squared is equal to 1. And again, that's coming from cos squared plus sine squared equals 1. We're going to go to number 7 next. So we've got a parametric equation here. We want to find dy dx. So really we're going to do dy d theta over dx d theta. dy d theta, 2's derivative is 0, sine's derivative is cos. Dx d theta, 2 cos theta would be negative 2 sine theta. So you could leave it as that. Free response, that would be full credit. Probably on a multiple choice, they'd have it neatened up. We could write this as negative 1/2, and a cos over sine is cotangent theta. Now, if we wanted to do the second derivative, we would do our derivative of the negative 1/2 cotangent, and then put it over our dx d theta. All right, we're going to go to number 10 next. So we want to find the length of our curve of this parametric. Well, first let's find dx dt and dy dt. Multiply the 3/2 out front, and you'll get 4t to the 1/2. For dy dt, that's a 2t minus t squared, so we'll get 2 minus 2t. So we will have the integral. They told us we're going from 1 to 3. So in arc lengths, we'll have radical. We'll have our x derivative squared plus our y derivative squared dt. So if we keep going, we'll have 1 to 3. We'll have square root of 16t. If we multiply this out, we'll have 4 minus 8t plus 4t squared dt. So this is really integral from 1 to 3, square root of 4t squared plus 8t plus 4 dt if we combine like terms. Well, we can pull out a square root of 4, making this t squared plus 2t plus 1. The square root of 4 just gives us 2. And t squared plus 2t plus 1 is really t plus 1 all squared. So I'm going to throw the 2 out front. Now the square root of a t plus 1 squared is absolute value of t plus 1. On the interval from 1 to 3, those will all be positives on the inside, so it just makes it t plus 1. If we had then, say, on the integral like negative 4 to negative 2, then we would have minus t minus 1. So then from there, we'll just do our antiderivative. We'll end up getting 9/2 plus 3 minus all 1/2 plus 1. 9/2 minus 1/2 is 8/2, which is 4. 3 minus 1 is 2. So this will be 6 times 2, so we get that the length is 12. I want to look at 13 next. We want to convert this to rectangular. So first we want to recognize we have x squared plus y squared, so that can be r squared, minus 2 times y is equal to r sine theta. That equals 0. Let's add the 2r sine theta over. And if you divide both sides by an r, we just get r equals 2 sine theta. So in this case, we would get choice A. So next I want to look at 19. So we want to do slope of the tangent line for this polar curve. So first, let's write out what x and y are equal to. X is equal to r cos theta, which means that x is equal to sine 2 theta times cos theta. Y is equal to r sine theta, which means that y is equal to sine 2 theta times sine theta. So to do dy dx, we've got to do our derivative of the y part, so a product rule. So we'll have cos 2 theta times 2 times regular sine theta plus regular sine 2 theta times derivative of sine, which is cos theta, over our dx d theta. So to start out, it'll be the same. Derivative of sine 2 theta will be cos 2 theta times 2, but now times regular cos theta, plus we'll have our regular sine 2 theta times derivative of cosine, which is negative sine theta. Now we want to do this at pi over 2. I like doing, or sorry, pi over 4. I like doing this with my parentheses. We're going to have something times 2 times something plus something times something all over something times 2 times something plus something times negative 1 times something. So just note we've already accounted for that negative by putting the negative 1 in there. Well, we have 45 degrees. That's 1 square root of 2. We can use that for the ones that are sine theta and cos theta. So sine of each of those will have 1 over square root of 2, and the coses are 1 over square root of 2. So we'll have, and let's put them in rationalized, I guess. We'll put square root of 2 over 2 here, 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 and here. And I wrote that one wrong. I got to fix. This is over 2. Now, the ones that are 2 theta, 2 times pi over 4 gives us pi over 2. Cos of pi over 2 is 0. So these will both be zeros. And sine of pi over 2 is 1. So these will both be 1s. So this is going to give us, since the first parts will wipe out, square root of 2 over 2 over negative square root of 2 over 2, or in other words, negative 1. And one thing you could do is you could graph this and just see if at theta equals pi over 4, roughly a negative 1 slope seems to make sense for the tangent line. We're going to look at 23 next. So we want the area that is inside this cardioid. Well, if you graph this and trace it, you'll find that this only goes from 0 to pi. That we'll need, and then we can just double it. So just so we can kind of visualize it, cos of 0 is 1. 1 plus 1 is 2. So we'll have 2 comma 0 for the first point. Pi over 2 will give us 1. So we're going to be right there. Then pi is going to give us 0. So this part's going to look something kind of like that. 3 pi over 2 is going to give us 1. So it's going to be something kind of like that. Or so my curves might be a little different. But essentially what we want to do, because we've got that sharp point there, is let's just find this area and we can double it. So we're going to have 2 times 1/2 integral from 0 to pi 1 plus cos theta squared d theta. And we'll leave you to do the rest of this. You'll have a power reduction and everything like that, but that's been somewhat recent, so hopefully you can handle that. We're going to look at 25 next. All right, so we've got, this has got a plus here. So it's r equals 2 plus sine theta. So in the first one, if this one here, if we put 0 in for theta, we get back 0. If we put pi over 2 in, we get back 5. And then, so that's 5 there. And then if we put in, actually, let me put that with a scale. And then if we put in pi, we're back to 0. So this creates basically a circle that looks like that. And you could just get that from your calculator if you wanted. Again, this is the other one that wraps around, 2 plus sine theta. So when you put 0 in, you get 2. When you put pi over 2 in, you're going to get 3. When we put pi in, we're going to be back to 2, so we'll be over here. When you put 3 pi over 2 in, we will be at 1, so we're down here. So it kind of looks something like that, and my scale might be a little funky, but something like that. So we want the area that is inside the blue curve, but outside the purple curve. So basically, we want this space here. Well, what we're going to do is we're just going to find this space and we'll double it. So we've got to do the blue one minus the purple one, and we're going to go from where they intersect to pi over 2. So to see where they intersect, we'll have 5 sine theta equals 2 plus sine theta. We'll subtract the sine theta over. That's 4 sine theta equals 2, or sine theta equals 1/2. So that means that's going to be theta equals pi over 6 is what we want. So we're going to have 2 times. We're going to have the blue one from pi over 6 to pi. So our area for that will have 1/2 pi over 6 to pi over 2. We'll have our 5 sine theta squared d theta. And then we want to subtract off our portion for the purple one. So minus, we'll have 1/2 integral pi over 6 to pi over 2. And we'll have the 2 plus sine theta squared d theta. And we'll leave this for you to finish up from there. So remember, the worked out solutions are all on Schoology. So as you're working through, you can check those. Try to focus on whatever ones you felt you had the most trouble with during the unit. Have a great rest of your day.